In this video, we're going to practice checking the necessary conditions for a hypothesis testing question and working through some of the calculation steps of that same question. So let's read through our prompt here. We've got a survey that asked a random sample of 850 respondents how comfortable they are with Facebook creating a list of categories that represents their interest for them. 41% of the respondents said that they are comfortable. We are wondering if these data provide convincing evidence that the proportion of American Facebook users who are comfortable with Facebook creating this list of interest categories for them is different than 15%. And the important thing here is we're talking about proportion. So our first step here, we want to set up what's our null hypothesis and what is our alternative hypothesis. So first thing, what is H naught and what is HA? That's the first thing that I want to do. So we said in this problem we were talking about a proportion, which means that the parameter that we're going to be using here is P. So for H naught, we're going to be talking about the population proportion P. Same thing with the alternative hypothesis HA. If I look at my alternative hypothesis to start, I'm going to look at what question are we asking, what claim are we making. And I'm going to look at this last sentence right here. I want to know, is this proportion different than 50%? So not less than, not greater than, just different. That means we're doing a two-tailed test. We're going to say different than 50%, which would be 0.5 as a proportion. And once we have our alternative hypothesis, the null hypothesis is always a statement of equality. It's going to be P is equal to 0.5. So we've got our null hypothesis, we've got our alternative hypothesis. That's everything we need to do in this first step. Step 2 says check that the necessary conditions are met. So the necessary conditions, the two things that we need to check are, first of all, independence. And these are actually going to be the same conditions that we saw for the central limit theorem for proportions. So we need to check independence, which again, that's very difficult for us to do. We're going to use random sampling as a proxy. So as long as we have something that looks like random sampling, we can go ahead and assume that our condition is met. Here in this case, we have a random sample. So yes, we can go ahead and assume that our conditions are met. And then for number 2, we have to check that success-failure condition. Success-failure condition. Now, for the central limit theorem, we used n times p. So we used n times p is greater than or equal to 10, and n times 1 minus p is that greater than or equal to 10. Now, in this case, again, with most of these types of questions, we don't know what P is, but we are making an assumption here. If we look at our null hypothesis, we said P is equal to 0.5. So a lot of times when we write out the formulas for these, we're not going to necessarily use P because that's generally kind of an unknown quantity. We don't want to say we know that for certain. But what we're going to do instead is we're going to say n times P naught, and n times 1 minus P naught. So we're using P naught in place of P, which P naught is just simply the number that we're using in our null and alternative hypothesis. So P naught in this problem is going to be 0.5. So anytime we see P naught used in any of the formulas that we require, that's coming from the null hypothesis H naught. So let's work through these here. Shouldn't be an issue, but we're going to go ahead and calculate it out anyway. Our sample size n, and actually we skipped that part, we said our random sample of 850 respondents, meaning n is equal to 850 in this problem. So okay, we've got, 850 times p naught, we said that was 0.5, so we can grab my handy dandy calculator and say, well, that is going to be 425, which is certainly greater than or equal to 10, so we're all good there. And then 850 times 1 minus 0.5 should also be 425, which is still greater than or equal to 10. So yes, our conditions are met. Again, if I ask you to verify that the conditions are met for a hypothesis testing question, I'm primarily going to be asking you to check this success-failure condition because that's the one that's more likely to give us a hard time. Independence is very difficult for us to verify, so in general, I'm not going to be asking you to check that. But you should be aware that that is a condition. Excellent. So we have our conditions, we have our null and alternative hypothesis. So now we're going to go to the next part, which says, okay, we would like to calculate the test statistic. If I want to calculate the test statistic, there's a couple things that I'm going to, well, at least one thing that I'm going to have to do first. I need to know, and let's just get some of our information down from our problem in front of us. We said P naught, that's coming from our null and alternative hypothesis, that's 0.5. We would also like to know what is P hat, what's our sample proportion. And I'm going to scroll up here, and they said 41% of the respondents. So that means P hat is going to be 0.41. So P hat is 0.41. And then I would also like to know what's my sample size N, and we said was 850. I think is usually pretty helpful just to have all this information written down so that we can reference it as we need to throughout our calculations. So for our test statistic, before we can find our test statistic, I think it's helpful to start by finding your standard error. So your standard error is going to be actually the same standard error formula that we saw for the central limit theorem for proportions. So that looked like P times 1 minus P divided by our sample size N. And again, we're going to run into the same issue that we did with the success failure condition, where we don't want to say we know exactly what P is, so we're going to call it P naught because that's just the number that's coming from our null and alternative hypothesis. So if we plug in these values, I've got square root of P naught, which is 0.5, times 1 minus 0.5 divided by my sample size N is 850. We want to be careful here because it is easy to make a mistake in our calculator. But if I divide this out, I ended up with 0.0171. I'm going to go ahead and round to 4 decimal places here. So there's my standard error. I kind of want to have that number first before we jump into the actual test statistic, because I'm going to need the standard error to find the test statistic. So we've got standard error, excellent. Now we're ready to find our test statistic. So let's do that in a different color. Our test stat is going to be, I like to write this out, our test statistic is going to be a z-score. So our test statistic when we're working with proportions is always a z-score. And I think that's really helpful to remember because then that helps us to determine what our p-value is going to be in the next step. So the formula for a test statistic, it's really just the same as the z-score formula. So we want the observation, which in this case is our p hat, minus our mean, which from our central limit theorem says that's p, or in this case p naught, divided by our standard error. We just calculated that in the last step. So we're going to take all the information that we have and plug this in. So p hat we said was 0.41 minus 0.5 divided by my standard error, which in this case is 0.0171. So if I calculate this out, minus 0.5 divided by 0.0171, I end up with quite a low test statistic, but that's okay, negative 5.26. So negative 5.26, this is the test statistic. This is what this question is really after. So part of our problem is going to be, okay, first we want to find our test statistic, which is helpful, and sometimes there are methods that you can use the test statistic to kind of finish up the process of a hypothesis testing question. But I tend to think it's actually a little bit easier to do one more step. So this last step here is we're going to find the p-value. So we're going to calculate the p-value. And in order to do that, I need to look back at what type of test we were doing. So if I scroll all the way back to step 1, we said we were doing a two-tailed test, so from our alternative hypothesis. This matters a great deal. So we're doing a two-tailed test. So a two-tailed test. And this matters because, so what do we know at this point? We know that the central limit theorem says that our sampling distribution of p hats is roughly normally distributed. We have a z-score of negative 5.26, so negative 5.26. But we said that this is a two-tailed test, so I want the area to the left of negative 5.26, but I'm also, in this case, because this is a two-tailed test, I want to find the area to the right of 5.26 as well, and then my p-value is going to be these two areas added together. So if I was doing just like a left tail test, then I wouldn't have to worry about this area over here on the right. If it's just a left tail test, I only find area to the left. If it's a right tail test, I only find area to the right. The two tail test is the only time I have to consider two separate areas. And again, I can use what I know about normal distribution and symmetry to help me out here. We know that our z-score is negative 5.26. So this is a z-score. We have our z-tables. Let's go ahead and consult those. So if I scroll back, look at my z-tables, I'm going to run into a slight issue in this problem. So we said our z-score was negative 5.26. And if I look right here, the lowest that I can possibly go from here is negative 3.49. Here's negative 3.49. And if I scroll all the way down to the bottom right here, I'm looking at this part right here. It says for z less than or equal to negative 3.5. So z-scores that are less than negative 3.5. Remember, our z-score was negative 5.26. It's very, very small. That means that the probability is less than or equal to 0.0002. Really, it should be less than 0.0002. We're just going to go ahead and assume, just for the sake of ease, we're going to assume that that area is 0.0002. So let's assume that this area to the left right here, and actually let me do this in a different color. Let's do this in red. This area right here is 0.0002. Now, that's one of the areas. We said this is a two-tailed test, which means that this area is also 0.0002. For this two-tailed test, you can do one of two things. We can either just add these two together and say 0.0002 plus 0.0002, or you could say, well, that's the same as just taking 0.0002 and multiplying it by 2 because we have 2 areas over here. So either one works. It doesn't really matter. Dealer's choice, whichever you're more comfortable with, but in either case, our p-value will end up being 0.0004. And this number matters a lot to us in our hypothesis testing question because it's going to be how we make our decision at the end of these problems. In every single hypothesis testing question, we either want to reject the null hypothesis or not reject the null hypothesis. And we'll talk about that in the next video. But this is one of the two numbers that we need to look at in order